Thanks everyone for being here for the last day, for the QPE day or the repeating nuclear transients day. I think by the end of the day you'll realize why we're having a full day dedicated to these transients in a TD conference. But really it's exciting that over my postdoc career I go from visiting theorists that don't know anything about QPEs to seeing this first simulation, so it's pretty nice to be part of this. So I was asked to actually present something very specific, so the connection of QPEs with TDEs. So anything related to, I guess, the memory models and precession will be covered by Johin over there later. I'll still be the first one presenting QPEs, so I'll go for a little bit of an introduction. So about at the end of 2018, I was hearing the story from Richard. Quick look data where we're being seen for 2018 data of this galaxy, which is actually not particularly interesting for other reasons per se. It's a small galaxy, fairly close. It was being monitored because in X-rays it was actually being very peculiar since 2010. It showed a Rosetta upper limit in the 90s and then an outburst with X-Lams Lu in 2010. It decayed over sort of a decade pretty slowly. And then in 2018, they saw a couple of X-ray flares in a short light curve. And obviously, they immediately asked for more and found that this behavior was repeating every roughly 9 hours. That's why they have a quasi in the name. And this behavior was never seen before in a galaxy, so it required a new name. The name was chosen to be quasi-periodic eruptions. I was told by Richard that Ari Lauer is to be credited or blamed for the choice of this name. And effectively, some of you know that I've taken the habit now of controlling on ChatGPT what the internet knows about QPEs for fun. So don't feel too bad if you don't know much about it. So essentially, I started maybe a year ago, and I can still proudly say that I can keep my job because AI cannot replace me. It's talking about volcanoes and magma. So I have the next contract at least. Yeah, maybe. But essentially, what's more interesting for me is actually that over the course of a year, ChatGPT started changing the answer to my opening. I hope you're well. And now it's actually telling me, oh, I'm doing well, thank you, how about you? And I can tell you, a year ago it was telling me, oh, I'm a machine, I don't have feelings, type of thing. And 2 months ago it was just saying, I'm doing well, without asking about me, so it's getting polite. And I feel like we should do the same, just in case. You never know. Yeah. So essentially now, after a few years of working on QPEs, we have a growing number in general of repeating nuclear transients, as Elias said. So for theorists, and actually for observers, it's relevant to ask a question, what is what? In particular, we have transients that recur every few hours, some that do every tens of days, some that recur every hundreds of days. And this can go on. I think the only limit is that the first surveys started taking data a few years ago, so I'm pretty sure in a few years we'll start finding stuff that recurs every few years too. The question is, how do I define QPEs in this plethora of transients? And the way I've chosen to move forward for now is to rely on the spectral shape during the eruptions, because the timing properties can be wild, but to me, what the sources do in outbursts during the eruptions should be telling us what's the physical mechanism driving them. So let's look at the first QPE that was found and exactly what it was doing spectrally during the burst. This is now a phase-folded profile combining all the bursts into one for high signal to noise, from quiescence to peak. And I want to remind you that these sources are actually detected, in most cases, when they aren't flaring. So there is an X-ray spectrum that is fairly constant within the single observation when the source isn't flaring, and it's consistent with the thermal spectrum with most counts below 1 keV, 0.7 keV. And I'll come to this later. The TDE people might find some similarities with a spectrum that looks like this in X-rays. And also during the eruptions, the spectrum doesn't become particularly hard. It's not like a Sagittarius star flares or an HM flare. The spectrum still looks like an exponential decay of a thermal spectrum. and it's very soft. This is 1.5 keV for this particular source, so there is no visible corona. And however, the way this spectrum evolves, it's not reminiscent of just accretion disk getting brighter and fainter. It doesn't really follow that trend. If you want to then go from now peak to quiescence again, they do effectively the similar thing, but I want to stress that this is not symmetric in energy dependence. And the X-ray nerds like me will see by eye that the green spectrum is harder here on the rise than during the decay, and the yellow too. But for people that are not X-ray nerds, you can visualize this by plotting, for instance, going from the start to the end of the burst. So you can plot, if you model all the emission with a thermal spectrum, you can plot the hardness or the temperature versus the luminosity, and you see that from start to decay, there is an hysteresis in the way the thermal spectrum evolves, so it doesn't just follow a diagonal back and forth. And essentially, you can picture this as the rise being harder than the decay at the same luminosity. And being this model a black body, this means that effectively the radius of the emitting region is expanding during the burst. If you want to model this with a black body, obviously this is a model-dependent answer. But this is a specific, if you want, energy evolution during the burst. That if this is a black body, the emitting region is expanding from the start to the end. So now we want to know how many sources we know of publicly that follow this spectral evolution, and there are 6 that are publicly known. The first one was found in the archives. Basically, people have been looking for X-ray flares in the archives, and then this source has been followed up again until last year. This is work in preparation by Margherita Giustini. The theorists might gasp at the diversity of bursts that you see in this light curve. This is the final boss, admittedly. This is the most complicated source, perhaps, to model. But I want to assure you that Margherita is trying and succeeding in finding a little bit of order in this chaos, and this paper should come out soon. But then, is this a QPE? Yes, if we define them as something that repeats and that follows the same energy evolution. This is, again, luminosity and temperature from start to decay, and this is the radius of the emitting region. So same relationship during all these bursts, even if they are fairly chaotic, and GSN069 is fairly regular. The bursts are emitted in the same way. Then there are 4 others that I discovered with Rosetta. You see just a collection of the timing properties. They're pretty different. Recurrence every couple of hours, pretty regular. Recurrence every day, pretty irregular. This is also 20 hours, and we don't have as much data. And you can see here a little bit of diversity in the amplitude and recurrence in the last one, QP4. But plotting the same energy dependence, you see the same. So there are wildly different properties in terms of timing, but the eruption in all the sources and in the same eruptions of the same source, different eruptions of the same source, they follow this clear energy dependence in hardness and luminosity. So despite the differences in the timing, the spectrum during the eruptions of all these sources behave the same. So it kind of speaks for a common physical mechanism. Now there are a few more candidates, which I'm cautiously calling candidates. But as Richard said, they don't talk like a QPE yet, but maybe we don't know the dialects of QPE language. But effectively, perhaps the best we have is J0249, found by Johin in the XMM archives. This is only a candidate because this is as many secure eruptions that we found, so 1.5. Now the positive thinking among us will think that this is a repetition, but formally we haven't seen fully the second burst, so I want to be strict. So this is a candidate. However, the spectral behavior during this eruption is exactly the same of those QPEs, so this is a particularly strong candidate. Then we have Tormund, that was an optical TD found by ZTF, and in an archival observation, it showed half a flare. We've never seen any second since, or the end of this behavior, so clearly this is a candidate, although at least from sort of quiescence to peak, the evolution seemed to be promising, but this is obviously pending more data on the source. We have this Swift source J0230, which repeats every 20 or 30 days. So the repetition and the X-ray phenomenology and the timing is reminiscent of QPs. However, the spectral evolution is different. The spectrum keeps getting hotter from rise to decay, so it never cools back when the source gets fainter. Again, is this a different dialect for QPs, or is this something else? Let's wait for more confirmation, for more data. So if we use the first 6 sources for a tiny population study, we can plot, for instance, what's the recurrence times versus the duration of the bursts. And apart from some sources that show a bit of a wild diversity in the way they recur, you can see a tentative correlation between these 2 quantities. So timescales correlate. And in this case, you see the peak luminosity versus the recurrence. And in particular, you can span a couple of orders of magnitude for the same recurrence time. So these 2 quantities are not correlated based on current data. And to me, this speaks against something related to accretion, because I would expect peak luminosity and timescales to somewhat be driven by the black hole mass, under the assumption that they have a similar accretion rate, which they probably have. In general, as part of the behavior during the eruptions, so far we only know that they emit QPEs in X-rays. There hasn't been any multi-wavelength counterpart to the flaring state of any of these sources yet. We have usually UV and optical data in simultaneity with X-rays with XMM. We have undertaken radio campaigns during the bursts, and we haven't found any evidence. Now, at most wavelengths, these are low mass galaxies. Most wavelengths, the galaxy sort of dominates the emission, especially in the optical UV and infrared. So we have to go to space, which took a couple of proposal runs to do, and we are still processing the data for what we have. It's a hard exercise, but at the very least, there aren't prominent flares in any of the other wavelengths. If they are present, they are very faint. Radio variability? No. But Adele probably knows more. Yeah. So, no. Yeah, so what are they? We've heard a few interpretations from Elliot. I think I'll just show 1 or 2 slides, actually 1 slide, with a collection of the models for your reference if you're interested in knowing exactly what has been proposed so far. Some accretion disk instabilities or disk tearing, QPEs as the outcome of partial TDEs at the pericenter, where perhaps the latest model that tries to account for the presence of an accretion disk is Wembin's and Elliott's model. And others that propose that QPEs are pre-existing extreme mass ratios, secondary objects from extreme mass ratio spirals. And the accretion disk they're interacting with comes from a TDE precursor. So for this conference, and the connection between QPEs and TDEs, I'm going to focus on this prescription here, but this, alternative models may exist. We'll hear a lot more supporting evidence that this makes sense from the speakers today, or anyway, mechanisms are related to a system like this. But for the moment, I'll try to just outline the connections between QPs and TDEs observationally. So, driven by data mostly, really. Okay, so in particular, let's not forget that these are the right galaxies for all this mess to happen, because we have evidence that these are low mass supermassive black holes, of 10 to the 5 to 10 to the 7 point something. In low mass galaxies, obviously, these are very uncertain estimates. They don't come from any direct estimate. They come from galaxy scalings, which are poorly constrained at the low mass end. And in fact, we want these transients to constrain these relationships. So it's pretty circular. That's also why I'm kind of putting like a circle and giving you ballparks. We don't want you to get fixated on a black hole mass at the moment. It's not particularly relevant. They're low mass. These galaxies are also, the QPE galaxies are related to post-starburst galaxies. The sample size is small, but Thomas has found a preference for post-starburst galaxies in this small sample. And for the couple of sources for which this was possible, there's evidence of a nuclear subcluster. All these ingredients, in principle, should enhance the interactions between stellar objects and the central black holes in these nuclei. So these are the right galaxies for stellar dynamics to do its best. regarding the X-ray properties in quiescence, so I'm taking out pretty much the QPs from the rest of the few slides from now on. The quiescence, as I said, is a soft thermal spectrum, indicative of the emission from basically close to the innermost stable circular orbit in a low-mass black hole. And, as much as low-mass AGN could give you this, because, effectively this is the tail of the accretion disk from a low-mass black hole, regardless of what you want to call it. Usually AGN have an hard X-ray spectrum too. If they have been accreting secularly, they usually show a persistent X-ray corona, which hasn't really been seen in any of these sources in quiescence. Again, forget about the eruptions for a while. Now, if I have an accretion disk spectrum at around 10 to the 41, can I detect also a power law 100 times fainter? Maybe not. So it's hard to say based on the data, but we don't have evidence of any hard emission. So these accretion flows look more TDE-like than AGN-like based on the spectrum. Regarding the long-term evolution of the X-ray quiescence, again, I'm showing the QPEs, but forget about them for a second. This is the X-ray flux excluding the QPEs in the discovery source. 2010, it underwent an outburst, it decayed, QPEs started to be observed, then there was a brightening of the quiescence, QPEs disappeared, the source went faint again, QPEs reappeared again. So it's a very dynamic system, and X-ray TDEs are probably the least known kind of TDEs. So if you see a decay with a soft X-ray spectrum in a galaxy, which is low mass, you're tempted to call this an X-ray TDE. Obviously, there is less evidence than for optical TDEs in which you have spectrum and whatnot, but this is reminiscent of an X-ray TDE prior to the emission of QPEs. This decay in the quiescence has been seen in other QPE sources. This is now EuroQP3 again. This is the flux of the source, which includes data from the peak, the eruptions in yellow, but really focus on the quiescence in dark red. We only have 2 detections in 2020, and then the quiescence was never detected since, including a very deep upper limit with XMM, a factor of 100 fainter than 2 years before. So this accretion flow onto which we see QPEs fairly regularly for a couple of years decreased quite fast. I don't want to fit the slope into points, but it was very steep decay. I can't tell you the slope. In the best QPE candidate we have so far, we have seen exactly the same. QPEs were found on top of a decaying overall trend in X-rays of a couple of orders of magnitude. This is an XMM observation in 2001. There were no QPEs. It's a very stringent decay. You can fit it with a power law. If you're part of this conference, you're probably going to be happy. But you can see that QPEs were seen in 2006. There is some variability on top of this decaying trend. This is swift, so you can't really say much. If you are optimistic like me, you can say, okay, maybe the high amplitude flaring behavior has persisted and we've just missed it. Again, this remains a candidate today, but still yet another source with an X-ray decay of the quiescence emission onto which we see the QPEs. Although this hasn't been seen in all the sources. There is another source for which we have X-ray data dating back to the 80s. This is the source which showed a lot of repetition, a lot of difference in recurrence in the flares. It's an X-ray source since the 80s. The emission is pretty constant over 40 years. But I want to, if I told you that I can exclude the presence of a nuclear transient with a baseline of a point every 10 years, you would laugh in my face, I guess, right? That's not how we are designing the next generation of service. We can all agree on that. So this is clearly not the best flight curve to rule out anything, really. So I guess absence of evidence isn't evidence of absence. We can't really say much. In other 3 galaxies, we have no data before the discovery of QPEs, maybe a Rosetta upper limit. So we can't say really what happened in the nucleus beforehand. So really, for the sources, we have some data. We've seen an X-ray decay. For others, we just don't have any data. So it's probably too much of a coincidence. In a source for which we don't really have any detections before the onset of QPEs, again, lighter colors here, the flux of the peak of the QPEs, focus on the darker points for the emission of the quiescence. It was undetected in the first Rosetta scans, even when the QPEs were found. And then it was detected by XMM a factor of a few or 10, brighter than the first upper limit we have. These are all 3 sigma upper limits. So in this particular case, we can't say exactly what happened, but at least the accretion flow is short-lived. It started appearing or being detected after the onset of the QPE behavior. So it's not particularly older than the start of QPEs either. And regarding multi-wavelengths, evidence that supports a past TDE, we have a bunch of interesting data for the discovery source GSN of 69, the one that showed a nice X-ray decay. The UV spectrum from HST suggests an anomalous carbon-to-nitrogen ratio that some Sheng et al. Have suggested could be evidence of a past disruption. And Wenbin and Kishore Patra have checked the optical images of Hubble, and they found that the O3 map is decomposed in a nuclear and an extended component. And the age from the nuclear component points to short-lived accretion in the nucleus of about less than 10 to 100 years, pretty consistent with the decay 15 years ago. So again, not the smoking gun for a TDE, but all this is a little bit too much of a coincidence for just a handful of QP sources to have so many connections with TDEs. Now, the candidate for which we found half a burst was found on the decay of an optical TDE. This is Tormund. Clearly, I don't want to necessarily say that this was a QP because we saw half of a flare, but I want to point out how similar it is to an eruption of Euro QP1 in terms of time scales and amplitude. And so, I mean, this is pending confirmation, but we have evidence of a potential QP-like behavior in an optical TDE. Again, a handful of galaxies, and they're all sort of connected with, if you want, weak evidence, but they're all connected with TDEs. Another QP candidate that I haven't mentioned before, this is a X-ray and infrared TDE confirmed as such by an optical spectrum. You have now the X-ray light curve, non-detection in EROS-1, then the start of a flare and a decay based in X-rays, coincident with an infrared echo. And we have an XMM non-detection here, which is pretty deep, which sort of constrains that there was a pretty strong decay. But there have been a few points indicating that the source underwent some amplitude variability. In particular, the Rosetta data in the last survey tell you that the variability happens over just a few hours. This is less significant than the Rosetta QPEs, so it's less constraining, and also we have non-detections of QPEs in XMM, but this is still, again, a TDE, which is confirmed by the optical spectrum and by the infrared echo, for which we have seen QP-like variability. And again, now this is a collection, if you want, of weak to moderate evidence that connects QPEs to TDEs, but there is a piece of connection in each of these handful of sources. So I'm pretty sure the people at this conference will be convinced that there is some sort of a connection observationally with QPEs having a precursor of TDEs. But if you still want to be healthily skeptical, and if you think I'm being delusional, wait a few hours because Matt Nicol will clarify all your doubts about this connection. Now for the last more than 5, I guess, if you didn't warn me, that's good. Yeah, that's fine.
You're fine.
Okay, cool. I want to talk about the rate of quasi-periodic eruptions. This is particularly relevant regardless of what they are. They're an interesting nuclear transient, and we want to know how many there are in the sky. So I've used the 4 QPEs discovered by Rosetta merely because they are part of the same survey for which I have control of the detection efficiency. So I could control the observed numbers and produce intrinsic numbers. This is now the number density on the left y-axis as in unit per megaparsec, on the right y-axis in unit per galaxy with the stellar mass range. And you see we have 4 objects, 3 bins, a very uncertain fit for a very steep power law. Similarly, I guess to TDEs, some consistently being to the -2. Now, what this tells you effectively is that I can only constrain the abundance of QPEs because QPEs outlast my survey. I can't tell you a formation rate. This is an abundance rate. Using these galaxies, we have either, well, the 1 every 10 to the 4 galaxies emitting QPEs, or the rate of abundance per volume is 10 to the -6 per megaparsec cube, using these 41 + 7 as a lowest luminosity value to which we are sensitive, which comes from simulations as well. A very uncertain number. I'm giving you a ballpark because you can already see integrating this function, that the uncertainties are an order of magnitude. But this is already quite useful because it's the first, if you want, data-driven volumetric rate estimates of QPEs. And now we can compare it with other transients. Now, caution, because the lifetime of QPEs is unknown. And if I want a formation rate, I need to divide the abundance by the lifetime. So I'm keeping it as a free parameter on the x-axis. So this is now the formation rate of QPEs in green as a function of the lifetime, compared with the rates, the formation rates of TDEs. Again, caution, because, for instance, I cut this luminosity function at 42.5, like the X-ray TDEs. But even if there is a connection with TDEs, TDEs make it into a luminosity function for their peak luminosity, QPE make it in a luminosity function for their eruption peak luminosity on top of a quiescence that even if it's related to the TDEs, it's not at 42.5. So it's really hard to relate these numbers with one another. If you want this is maybe a pessimistic rate comparison with TDEs, so it tells you that basically there is one QPE every 10 times the lifetime TDEs. So if QPEs last 10 years, it's one every 100-ish. If QPEs last 100 years, is one every 1,000-ish. But if then again I integrate the full range of the QP luminosity function, assuming that if there is a TD, no matter the wavelength it's been detected into, there is an accretion disk. Even if I don't see the X-rays, there is an accretion disk with which the emery could collide, then this tension is much smaller. So if you want to take this as a range of ratios, QPEs to TDEs, this is a problem I made yesterday, just for motivating discussion. In this case, you would have roughly 1 every 10 if they last 100 years, so a much higher abundance of QPEs in precursor TDEs. Something reasonable will probably lie in between, so maybe 1 every few tens. But again, we know so little that I'll probably adjust this number based on what we find rather than the other way around. Something else that we can do, regardless of the TD connection, is that if QPEs are emery, the rate of QPEs will give you the first ever constraint on the rate of emeries that Lisa will see. Now, by definition, the QPE rate will be a lower limit to the emery rate, because even if they are emeries, not all emeries will be detectable as QPEs, but if we see as many QPEs, there are at least as many emeries. Way more, but at least as many. Now, even if QPEs are emeries, we don't know whether they're stellar emeries or black hole emeries necessarily. So you have to make all sorts of different extrapolations. So we have in gray here, in the gray shaded area, the Lisa predictions for events per year from black hole emery, from Babak et al. So this is why the exercise is useful, because it spans more than 3 orders of magnitude, what Lisa can see. And if QPEs are black hole emeries, obviously the numbers are pretty stringent because we know them pretty well. So the constraint would be fairly stringent. It would mean that there are a lot of emeries, more than they've predicted. If QPEs are stellar emeries, thanks to Itai, actually, we tried to do some corrections to relate to the black hole Lisa emeries. The constraint is less stringent. This is a 1 sigma interquantile range as a lower limit. So depending exactly on where the value is, QPEs could be very little stringent or potentially somewhat stringent. They would rule out the pessimistic emery models. So either way, if QPEs are emery, at least they made a fair uncertainty estimate on the rates, and they will still be 3 orders of magnitude. But in the best case scenario, we can rule out the more pessimistic models and actually give something pretty useful to the Lisa community as well. Yeah? Yeah. This is I think this is the events per year that Lisa will detect. And I converted it using their redshift completeness with my rates. And this is a more direct number, because if QPEs are black hole emeries, I don't need to do any further conversion. This is much more uncertain, because if QPEs are stellar emeries, I need to translate the number of stellar emeries to black hole emeries, and this is more uncertain. Yeah. So QPEs could be pretty useful for Lisa if they're emeries of either kind. I guess I'll leave you with my summary. I see you standing here. QPEs are very interesting. We have a handful of sources. They are being connected with TDEs, and the model under investigation is that of extreme astration spirals, but we need to do some more work, and I'm happy to take your questions.
Okay, using my prerogative again. So I think it's in DSN 069. So to preface this, I mean, even though I agree that it's unlikely these are powered by accretion, it's hard to believe that the disk, being hit by the star, as Elliot described, isn't having some impact that could propagate down to the quiescent source. So my question is, I think it's DSN 069, there's a claim of a QPO, some rise in the flux between the flares, which is about the ballistic trajectory time to the central black hole. So my question is, do you see any QPO type behaviors in the quiescent emission in any other sources?
We haven't, but again, QPOs are unbelievably hard to find in anything that is an X-ray binary. It's already curious that at least one source out of 6 has shown QPOs.
And it's probably one of the sources with the brighter quiescent, so they would enable that.
Not necessarily,
detection.
actually.
Okay.
There aren't that many other sources for which you can do the same exercise. That's fair. That's the one. That's the source with the highest number of observations. So the baseline and the coverage is the highest, but it's not a matter of brightness. It's basically amount of data. Okay. So yeah.
Thanks, Elliot.
Maybe DJ, if you want to go
DJ,
ahead.
sorry. Okay, should we go to Zoom first? Yes.
Hey, Riccardo.
Hi.
Nice talk. Just a quick question and kind of comment. Supermassive black holes that accrete vary on all time scales, right? So we have to be really cautious when claiming QPEs based on just a few scattered data points. I mean, you said this, but I just want to stress it again, that they vary all the time. This was, done 20 years ago. The claim about QPEs, the same thing, right? You have to be really cautious before claiming something is truly quasi-periodic, just based on few cycles and few flares that are poorly sampled.
Yep. Only the ones that have shown a flare in an XMM light curves twice have been considered QPE sources in this talk, in fact, yeah.
Yeah, but the Baldini source that you showed, that one just looks very stochastic to me.
Yeah.
Yeah. And also another comment about ChatGPT. By the way, if you try QPEs on Gemini, it totally nails it. We are out of job.
Oh.
Yeah.
Elliot.
So, thanks, Riccardo. I was curious about the source that's been on for 40 years.
Yeah.
Do you know, is there host galaxy narrow line spectroscopy? Because that would be a particularly interesting one to study.
It's one of the 2 galaxies that are on the CIFER side of the VPT.
Okay.
We haven't found, I think, I'm trying to think whether there is HST imaging already. I think it's the one for which we've seen the evidence of a nuclear subcluster.
Is there IFU data?
It's the, yes.
Okay.
And
okay,
yeah,
great.
Thomas will say more. And actually it's the one source which is the only one with a radio source, which is surely not star formation. And it could be consistent with the low luminous DAGN. So for that source, the jury is still out there as to what it is at this time. So yeah, there doesn't have to be a TD in all the sources of precursor. There has to be an accretion flow, and I guess the TD, subclass could be more likely just because there are more inactive galaxies than active galaxies, as you said.
Thanks.
Itai?
Very nice talk. So you clearly presented the evidence that QPEs tend to perhaps be associated with TDs. And I guess, you also discussed their rates. But I guess my question is, what would need to happen for us to make the opposite association in terms of constraining the fraction of TDEs that are being followed by QPEs?
From the data point of view, well, I mean, the problem, ideally, you have an XMM orbit on every TD, no matter the wavelength, at different epochs. In practice, this can be done, and even you could do a whole conference trying to relate the X-ray TDs with the optical TDs. By its selection, X-ray QPs are found in sources that are, if they are TDs, X-ray TDs, because you see the X-rays. So the first exercise I've done was trying to compare with the rate of X-ray TDs only. If anything, I don't think you can learn more about TDs from QPs necessarily, if TDs are what you need to see the emery that gives the QPEs.
Maybe I can ask slightly, are we limited by follow-up resources or by number of TDs that are bright enough in the X-rays or soft enough that you would be able to see?
I think resources.
Resources, so we just need them to give you more time to follow up with long baselines, X-ray TDs.
Yeah.
Okay. Vikram.
Yeah, really cool stuff. I'm curious about your sensitivity to longer timescale QPEs, sort of a few days to maybe 10 days. In the elucidate search, does it sort of go down linearly with period, sensitivity?
So effectively, there are obviously biases in the way I found the elucidate QPEs, because if, I have a set of 10-ish points separated by 4 hours, separated by 6 months. So I find stuff that repeats within a day or two of baseline, but also stuff that could have appeared over the baseline of 6 months. So if a source, if its duration doesn't exceed my baseline of 1 or 2 days, I can still find a flare in one survey and one after 6 months, and its period can be anything, any fraction of 6 months. There are some biases, but they're not as bad as you may think.
So do you think it's significant that you don't see things beyond 20 hours? So
not really, no. I think it's still, even if the tail of this is at 5 days, we're pretty biased and you can't follow them up. Or if I do, which I've done, there are some candidate sources with some variability, then you shoot 100 kilosecond XMM, it's empty. Sure, you can argue that the repetition is more than 30 hours, but who would give me 300 hours to test it? So it's, we're limited by that for sure.
Yeah, I wonder about your estimate about the emery rate, the connection between QPEs and emery. Let's say given some of the models based on main sequence stars are right, and then how do you actually, let's say the orange shaded region, how do you go, because there are, we know the currently bright QPE sources, we know their number density, right? And then maybe some of the stars are still orbiting, but they're not erupting.
So yeah, that's why I would consider all these very uncertain band as a lower limit.
So the lower limit is only based on the erupting ones.
Yeah.
Right. So there could be, right, there's some dark main sequence emeries are there, but they have not undergone.
Yeah. I think that's why it's still useful to do, even if we know nothing about QPs and very little about emeries. It's because at the very least, this is a lower limit, and it might actually be already constraining.
That's right.
We need to shrink these uncertainties which come from my rates and from the extrapolations between stellar and black hole emeries. But if we manage to do that, even if you have like a lower limit at this level, whatever the lifetime is, you already rule out the most pessimistic emery models for LISA, which will make people happy anyway.
Yeah, so there's a good hope in pushing it up.
Yeah.
Right.
I think I tried to make an effort, at making this band fairly wide on purpose, just to give you the idea of how little constraint there is. But already, I think it's very unlikely that there are, if QPs are less emery than the pessimistic model they're using. So it should be definitely more than that.
Yeah, thank you. Yes.
All right. Let's thank Riccardo again.